Hello, students. Have you ever wondered why oxygen molecules are so vital for our breathing? Or how two hydrogen atoms can combine to form the simplest molecule? Let's talk about homonuclear diatomic molecules, molecules made up of two identical atoms. These molecules, like H2, O2, and N2, are the building blocks for a lot of the chemical processes we observe in everyday life. These molecules are held together by covalent bonds formed by the sharing of electrons between atoms. As we break down these molecules with molecular orbital theory, we can understand their behavior and properties, from the oxygen we breathe to the nitrogen that makes up most of the air around us. So, let's explore how these tiny bonds create the world we live in. Let's start with the simplest one, the hydrogen molecule, H2. Imagine two hydrogen atoms, each with one electron in their valence orbital. When they combine, their electrons pair up and occupy the sigma-1s molecular orbital. This results in the formation of a single covalent bond. The bond order here is a half times the difference between the bonding and antibonding electrons, which gives us 1. So, we have a single bond in H2. With a bond dissociation energy of 438 kJ per mole and a bond length of 74 picometers, this molecule is quite stable. What's interesting here is that since there are no unpaired electrons, H2 is diamagnetic. This means it won't interact with a magnetic field, a fascinating property that molecular orbital theory helps us predict. Now, let's talk about the helium molecule, He. Helium is a special element with its electronic configuration of 1s squared. So, if we bring together two helium atoms, we have 4 electrons in total. These electrons fill both the sigma-1s orbital and the sigma*1s orbital. Now, the bond order here is calculated as 1/2 times open bracket to minus to close bracket, which gives us 0. This means the helium molecule, He, does not exist. Its bond is too weak because the antibonding interactions outweigh the bonding interactions. This concept is key when understanding why some molecules, like He, are unstable even though the atoms involved are stable on their own. Next, let's explore lithium. Lithium has the electronic configuration of 1s squared, 2s1, so in a lithium-2 molecule, we end up with 6 electrons. These electrons occupy the sigma-1s orbital and the sigma*1s orbital, along with the sigma-2s orbital. The bond order here is 1/2 times open bracket 4 minus to close bracket, which gives us a bond order of 1, indicating a stable molecule. This is a single covalent bond. Since there are no unpaired electrons, lithium-2 is diamagnetic. Interestingly, lithium-2 molecules exist in the vapor phase, proving that even though we are working with elements that seem simple, their bonding behavior leads to stable molecules under certain conditions. Now let's talk about carbon, or C2. Carbon has an electronic configuration of 1s squared, 2s squared, 2p squared, which gives us a total of 12 electrons for the C2 molecule. The molecular orbital configuration for C2 is open bracket sigma-1s close bracket squared, open bracket sigma*1s close bracket squared, open bracket sigma-2s close bracket squared, open bracket pi 2p sub x equals pi 2p sub y close bracket squared, which tells us there are 4 electrons in the bonding pi orbitals. So the bond order here is 1/2 times open bracket 8 minus 4 close bracket, which gives us a bond order of 2. This means C2 has a double bond between the 2 carbon atoms. Remarkably, C2 is diamagnetic even though it has a double bond, because all electrons are paired. This behavior is quite different from what we see in other molecules, where a double bond typically involves a sigma and a pi bond. The fact that C2 is diamagnetic shows how bonding can vary depending on the distribution of electrons. Finally, let's explore the oxygen molecule, O. Oxygen atoms have the electronic configuration 1s squared, 2s squared, 2p to the power of 4. And in the O molecule, there are a total of 16 electrons. These electrons fill the sigma 1s orbital, sigma star 1s orbital, sigma 2s orbital, sigma star 2s orbital, and the pi to p sub x and pi to p sub y orbitals. But what's interesting here is that the O molecule has two unpaired electrons in the antibonding pi star orbitals. This gives the bond order as 1/2 times open bracket 10 minus 6 close bracket equals 2, indicating a double bond. But here's the twist. O is paramagnetic because of those unpaired electrons, meaning it's attracted to a magnetic field, something that molecular orbital theory predicted and has been experimentally confirmed. This paramagnetic behavior is a unique property of O, which plays a critical role in processes like combustion and respiration. Let's quickly recap what we've learned about bonding in homonuclear diatomic molecules. From the stable H with its single bond to the unstable He, we've seen how the arrangement of electrons in molecular orbitals determines the bond order, stability, and magnetic properties of molecules. We also explored how oxygen and carbon differ in their bonding behaviors, highlighting the importance of understanding electron configuration in predicting molecular characteristics. Whether it's the diamagnetism of C or the paramagnetism of O, molecular orbital theory gives us a deep insight into the invisible world of atoms and their bonds. I hope this session helped you see how these fundamental principles shape the molecules around us. See you in the next class with more fascinating reactions and real-world connections.